Okay, so we've got another AMA or just kind of interview session for Nexa with Andrew Stone and myself, Paul Church. So we're gonna dive into a bit more of a kind of technical discussion today, or maybe even more of a lecture about script templates and how they are used in smart contracts and transactions more generally on Nexa, because there is something quite unique to Nexa that opens up quite a lot of different possibilities. So yeah, so welcome, Andrew. It's great to chat with you again.
Hi, great. Yeah, so I thought it might be fun to like arrange these a little bit as like some question and answer if the community has questions, and then also like a topic, every time we come on. So this time it could be about script templates.
Right, I think that's a good way of doing it.
Yeah, yeah. Okay. So guys, I have, my iPad here. So if I'm looking down, it's because I'm writing, right? And because script templates are kind of complicated, I thought having some diagrams might make sense, right? So just to jump, should I just jump right in?
Yeah, go for it.
Okay, so let's talk about like the purpose first, right? And essentially, like, what are the sort of major advantages of the script template system? And basically, there's a couple of issues that have come up with, in our understanding of UTXO set blockchains and so forth, and script templates attempts to address these issues. The first issue, maybe to think about, is we want to get like the UTXO set as small as possible. So rather than putting very long scripts in the UTXO set, we actually want to push them. We want to actually push the data to when the script is evaluated, not when it's just sitting in the ledger. So that's one issue. Another issue is like if you ever use Bitcoin or something and you want to send like a Bitcoin address, it can only be a certain set of addresses, right? Like a certain address type. It can be pay to public key hash, right? Or pay to script hash, right? And in this sense, pay to script hash is doing something similar to script templates, is in that if you wanted to send, like, if you wanted someone to send you money, but the you that you're talking about is a very large contract, then how could you send them that entire contract, right? And then also, even if you could inside like some gigantic address format, why would you want the person who's sending you money to sort of be told all the gory details about your subsequent spend, right? Because it's interesting, like the contract that the address that you send to constrains the next spend, right? So the person who's sending you money shouldn't care about what the next spend is going to be, right? And so similar to P2SH, pay to script hash in like Bitcoin, what we want to do is give the person who's sending us money like a very succinct description of where to send, not an entire smart contract. Okay. So then finally, there's a DOS attack vector, which we can also avoid, and I can go over that with script templates. And then it also lets you, if you sort of move into more smart contracts, one of the key features of a smart contract is this concept of a covenant. People talk about, maybe use different terms, but the idea is that the life of the smart contract should exist for longer than just one spend, right? Now, I mean, that's sort of really unintuitive to people, but like in UTXO set, blockchains, unlike Ethereum blockchains, you execute a contract and receive permission to spend in a transaction. And then once you have permission to spend those coins, then you, as the transaction who got permission to spend, can create any child constraints that they want. So in order for a contract, like a smart contract, to last across multiple transactions need a way to say, hey, you can only spend this input if your output also adheres to certain transaction rules, right? Certain script rules. So that's the basic idea of a covenant.
It's worth maybe pointing out like where the idea of a covenant actually comes from. I don't know if there's an earlier version of this, but I know this from property, that when you actually buy a property, often or sometimes there's a covenant as part of the contract where there's some kind of requirement, like you can't use land for business or something like that, but it stays in perpetuity. So when you buy it, you don't suddenly get rid of those rules. It just passes on through the owners through time. And that's the same thing as the smart contract.
Exactly. So no owner can say, oh, I don't want to follow that covenant anymore, right?
Right. The actual contract stipulates that it must be like this requirement must be passed on to the new owner, and that's essentially what happens in the smart contracts on Nexa.
Yeah, it's also another way to think of it is like one of these viral software licenses, right? Like GPL. Okay. So this is a key feature to creating smart contracts on UTXO blockchains, and we'll see that script templates makes that a lot easier. And in particular, what we need to think about is this sort of like reconceiving of the participants in a transaction. Okay, so in these blockchains, you used to think of it as two participants. You have the holder and then the spender, right? And these are often the same people, but see, they don't have to be. And we should think of it this way because obviously any entity wants to spend any holder's money, right? So really in the blockchain, these two entities should be considered separately, right? You have the entity that constrained to spend, and then you have the entity that eventually meets those constraints to spend, right? Okay. But now we actually have, so that's like a two-party interaction, right? But in Nexa, and when you start thinking about smart contracts, you actually have three parties that interact. You have, let's in a sports analogy, you might have the referee, which would be like the covenant holder, the entity that's enforcing the rules of this smart contract, the rules of the game, basically. And then you're gonna, again, have the spender and the holder, right? So there's three entities involved now instead of just two. And in classic UTXO blockchain architectures, there's no good place for those three entities to put their data, right? And so what you end up with is some rather awkward workarounds. Okay, so all right, so with that in mind, let me just jump in. Okay. Okay.
Go for it. Dive in.
Yeah. So let me draw like basically a transaction on this little notepad. So I'm going to draw like a block here. Okay. And remember, we have inputs coming in, right? So these are, I'm going to draw them in the reverse direction because these are referring to prior ledger entries, right? Okay. And then inside these inputs, there is there's the holder's script. And this is like the classic way you do it. I mean, you have the spender script, right? And then in the output, so here, you know what I should have done really? I should have moved this down. And then, so, this transaction, let's call it A, is spending B's output. So you're going to have, it's going to refer to this exact output. So then you're going to have the holder, the constraint, right? Script here, right? Okay. So this is the way it looks. So, so here's your first problem with this architecture, right? What if transaction A referred to, a huge number of previous inputs, right? And all of the scripts in these previous transactions were extremely large, right? So now in order to validate transaction A, you've got to load up the script. So you got to run on the blockchain. You got to load up all these long scripts, right? thousands of them potentially, and you need to execute them all, right? Just to discover whether transaction A is valid, right? Okay, but how much money is transaction A paying for their transaction? Well, that's basically proportional to the size of the transaction. So we have a problem here, which is that transaction A can pay very little money, but it could have like a lot of validation time, right? Be required. Now you can argue in the end it all balances out because transaction, B, C, D, E, and so forth all had to pay extra, right? But again, we're forcing the person who's paying you to pay a lot of money for these large scripts, right? And also like both in terms of size and how much is paid, transaction A is like from an amortized perspective, it's all being paid for, but transaction A itself is getting a huge discount and potentially consuming a lot of resources and paying very little fee, right? Okay, so what if instead of doing it this way, what we did is we put a commitment to the holder script instead of the actual holder script here, right? So so a commitment is like a hash commitment. It's, what blocks use and everything. Are you familiar with that term? It's basically,
Yes,
the
of course. Yeah.
cryptographic hash of, okay.
Yeah, it's like a fingerprint of data.
Yeah, exactly. So, it's secure, right? So we're going to say it's going to be the hash of the script here. And then, of course, the holder's actual script is, placed in the, you have to make this bigger. So now we have the spender script and the holder's actual script. Now, what we have here is basically like pay to script hash, right?
Right, I was going to say that, yeah. Mm-hmm.
Yeah, so, and to a certain degree, script templates are like a cleanup and a generalization of pay to script hash. So the first problem that you need to understand about pay to script hash is that it's kind of like a big cheat, right? So nothing in the script in pay to script hash actually says, oh, you should actually then execute the holder script, which I pushed onto the stack as an input, right? It actually like outside of the script's normal execution model, it says, oh, I've looked at this output, and this particular output happens to be formulated exactly as a pay to script hash output, right? Even though it in no way is it identified as such, it just follows the same pattern. And so I'm going to assume that any output that follows that pattern is actually pay to script hash, and I'm going to break the virtual machine model and cheat and say, given that that's the case, I'm going to look at the input right here, and I'm going to find this data that was pushed onto the stack, and I'm going to pull it out, and I'm going to execute it as if it was code. Okay, and all of this was done because it was sort of the minimum way to get something like this to work with these advantages. But boy, is it not pretty to have a program that looks like it does one thing, but it actually does something completely different because we've actually changed how the outside virtual machine, how the code outside of the virtual machine actually works, right?
Right. This is because there wasn't, should I say, in Bitcoin and therefore Bitcoin Cash, any way to identify types of transactions or types of outputs, I guess in this case,
right.
As a specific thing, as opposed to just looking at the output and going, well, that has that structure or architecture, so that is the type. Right. Okay.
Exactly.
That makes sense.
Yeah. So in this case, and then there are so because they did it this way, there are problems, right? One problem is, for example, the holder script has to be actually pushed onto the virtual machine stack. And, there's a maximum width of that. I think it's like 520 bytes or something. So now actually any P2SH script has to be, severely limited in its size, right? it's also very inefficient to do that. So yeah, so the first thing that we did is just say, hey, we're going to have different transaction output types, and one of them is going to be a script template. And when that happens, when you look at this data here, don't look at it and actually push it to the stack, right? We're just going to include pieces of data. Okay, so it's not items pushed to the stack anymore, it's just pieces of data. Okay, and so now let me get into what script template output actually looks like. So it's basically just going to be, so here's a transaction. All right, so the output is just going to be the group info if there is any. And then it's going to be a script commitment. And then it's going to be args commitment. And then there might be some public args as well. And that would be, arguments that are not put in a hash, but actually just there for anyone to read. Okay, and basically what we're going to find out is that the script commitment here is basically what the covenant is like. The covenant party is what the referee can specify. And then the args commitment is like what the holder does. That's what they can specify. And then of course, when you eventually spend this, so we'll now spend this script template. And when we spend it, again, instead of pushing stuff on the stack, we just provide the information needed. And so we're going to provide the actual, covenant script. And then we provide the actual, holders args. Holders, by args, I mean the arguments to the script. And then we also provide like the, the spenders arguments. This is kind of hard to write because I'm holding the iPad and writing at the same time. I got to figure that out.
You're doing a good job. Don't worry.
All right.
I can read it.
Okay. So it's perhaps best to think of this as, hey, like three separate, and the arguments, the holders arguments and the spenders arguments, those, they can actually, they're technically in the code scripts because they just go push data, push this data, push this other data, push this other data, right? So I might accidentally refer to them as scripts, but they're what we call push only scripts. They can only be data, okay? However, now I'm really going to throw a monkey wrench in there. They can only be data, but a piece of that data could be a little chunk of code, okay? So it will, so like if the holder wants to like constrain a spend via like multi-sig, it can create a little scriptlet as an argument, which is going to be a little bit of code, and it passes it. It's ultimately going to pass it into the covenant script, and then the covenant script will eventually, execute that when it says, oh, this transaction has met all of my constraints, right? So now let me see if the holder has any constraints, right? And then something like pay to script hash, you can't do that. So you basically have to anticipate what constraints the holder might want, typically just a public key, right? And so, if you're writing a covenant in the old style, it's highly constrained as to what, I said there were that there were like workarounds to sort of put, what is like really a three-party model into a two-party model that, other blockchains use. Well, that's one of them. They just say, well, all the holders have to constrain this via public key. You can't use like multi-sig or anything like that, right? Well, okay, I mean, that's probably a limitation that you might be able to work with depending on what, the covenant is, but it certainly isn't ideal, right? So understand that all these arguments that we're talking about could be little scripts that then the covenant script can execute, Okay.
Can I ask a couple of questions
Yes.
before you go ahead?
Yes.
So there's one thing that always keeps confusing me with this, which
Mhm.
is the definition of holder and spender. I think, I don't know if it's because I'm always forgetting like which entities these are, but so who is the holder? Like what defines a holder versus a spender?
Okay. So, and it is confusing because the holder and the spender are often the same person, right?
Right.
But
Yeah.
they're physically the same person. But the holder is the person who said, hey, I'm giving someone an address, right? And they're going to send, money to that address. And the point is that the holder is constraining the spend in certain ways, right? But they are effectively the owner of the coins, right? And then later, they may come and say, oh, I'm going to spend the coins that I've constrained, right? So now they are entering the role of the spender, right? Even though
Right.
they're
But
the
I'm trying
same
to,
person.
yeah,
This is really important because you have to
yeah.
recall that it's not like anyone, if anyone can spend your coins, they will, right? So to think of the holder and spender as the same person, even though everything works perfectly, they are, right? But to think of them as the same person is a very bad idea, right?
But that's
Because
what I'm trying to do. Yeah, I'm trying to think because normally you do think of them as the same person. You think the person who creates the address that people are spending money to is the same person who obviously wants that money to spend,
right.
right?
But
But
if
you
anyone
don't need to do
can,
that, right? Yeah.
right, because if anyone, in effect, the whole world is out there looking at this blockchain, trying to spend your money, right? So if anyone can spend your money, they will, right? So to think of the holder and the spender as the same entity, even though 99% of the time they're gonna be, if all works, out properly, um, is not, a great plan. But there are certainly cases where that's not true, right? Like I could, well, I could send something to a multi-sig, right? So then, if I'm the person who sort of originally set up this holding, right? Then, sort of I said, hey, let's put this to a multi-sig. So then when I become the spender, really, I have to do it with my multi-sig partners, right? So even there are sort of instances where the holder and the spender are separate, mostly because the holder deliberately says, hey, to spend this, I'm going to have additional constraints like, multi-sig.
I'm
Okay.
more thinking of situations like you set up I know this is obviously this would be very complex architecture, but think of like a DAO. So you set up a DAO, but the DAO gives some responsibility to some entity that creates a transact or an address, sorry, where the spenders are not the same people that created the address. So they're like delegating some funds or responsibility of funds to someone else. Is
Yes.
that the kind of
Yeah.
situation it might be used in?
Yes, it might be. And also like, remember too that, right. So if we think, so that situation is never going to be the case if it shouldn't be if we're talking about just a single public key, right? Because no one should be passing their private keys around, right? But in the case you're talking about, for example, these complicated scripts could say, hey, any public key of this group is allowed to spend, right? So now the holder and spender are definitely different, right? Or it could just say, hey, this is an anyone can spend UTXO, right? And so, back in the old Bitcoin days, people thought, well, anyone can spend UTXOs are trivial. Like, why would anyone ever do that, right? And the answer is in modern, kind of script design, they're actually they'll be used all the time. The reason why is because it would be anyone can spend so long as they meet other constraints, basically the constraints of the referee or the covenant, right? So you might have like imagine like a state machine that's traveling through different states, right? And so you would say, well, anyone who wants to progress this covenant to a new state can do so. So technically anyone can spend, but of course you can only do so in a legal way, right? In a way that the covenant allows. And we'll see that in like constant product market makers and so forth, right? Where anyone can interact with the CPM, the constant product market maker, and evolve its UTXO state from one, from now to the next thing. However, in that state evolution, the product of the two quantities of the two tokens has to be greater than a certain value. That's, that's the constraint of a CPMM. So
yeah,
right. So we will have situations where, the holder and the spender are different. Okay. So where were we? All right. So I think it's best when you think of script templates to sort of just forget about the details of how they lay into transactions and just think, okay, there's really three scripts here. The covenant script, or the template, and the holder script, and which is the arguments in the spenders script. Now here's so we talked about previously how one of the big issues of a covenant is to constrain subsequent spends to be that same covenant, right? Okay, so if you look at, so let's imagine that in P to SH, for example, all of the holders, so since there aren't three things in pay to script hash, right? All the holders data has to be stuck basically in the covenant, right? So, and then, we take the hash of the covenant and put it in the next output. So how in the code would you enforce that the covenant, that the P to SH script is the same, but say, there's a new holder. So it's the same script, but there's a new public key in that script. Well, certainly the hash is going to change, right? So you can't just say, look at the, the new output in P to SH, right? Because the new output is just going to be basically, hash of a script, right? And the script is gonna, be basically a whole bunch of, covenant constraints. And then eventually there's going to be push, the holder's pub key. And then there's going to be a check sig. All right. And so you see that the fact that the pub key has changed because you're changing, say, holders, in this case, means that the whole hash of the script is going to change. So how do you enforce that an output is the same actual covenant script when some constant in the covenant script changed? The answer is, what you have to do is you have to tell the spender, hey, you have to push the whole script of the next spend to the stack, okay? And then you have to tear that apart, and you have to basically rip out the top of it, and you have to verify that these constraints, right, are the same constraints, and anything that goes below too, by the way, that the covenant originally had, okay? And then you can, then you ignore the pub key in the middle, right? And then once you have all that, you hash all that up, and you verify that that whole script that was actually given to you is actually the hash of the particular output, okay? So you basically have to write code that completely analyzes and tears apart and divulges the next spend, right, to ensure that the covenant is enforced. So this is pretty tricky, right? But if we were able to just factor out the holder's changes, right, from the script, then instead of doing all that, we could just compare the hashes of the covenant script, basically. So you see, instead of having to do all this work in a script template, since the holder's arguments are factored out to enforce that the child covenant is the same as the parent, you just you can use transaction introspection to say, well, what was the hash of my covenant coming in, and I'm just going to compare that with the hash going out. Done, basically. It's like a memory compare. So enforcement of covenant is a lot simpler in script templates.
That makes a lot of sense because I mean I know from using Cache script and then looking at all the bytecode that it does exactly what you said. It does like a huge map operations to just take all the data apart to actually. I mean it did it for introspection as well, but yeah, to actually just do the covenants, it yeah chops up all this bytecode and actually like I had to identify where the pub key was and then yeah remove the sorry, take the pub key out and then leave the rest of the bytecode to actually check it.
Right.
Which is yeah, it made the contracts really complicated. I mean, it was easy obviously to use the software, but the actual contract itself was massive for having to deal with that.
Yes,
Um,
and you're divulging the subsequent spend script as part of, this validation, and you're kind of limited to a pub key, right? Like you couldn't have any script inside the holders area. So there's various limitations, and then you spend all this time and complexity working on that, and you can't actually get anything done, right? So one thing that we need to understand here is that with Ethereum being like a Turing complete machine, there's not going to be any miracles, right? Like the script template system is not like a miracle that lets you do something that no one's ever been able to do before, right? Because it can only do at the maximum what a Turing complete machine can do, right? What we're talking about is being able to do this very efficiently, and more reliably, and also perhaps more privately, right? So, okay. But there is one additional feature, that at least P2SH style covenant systems can't do, which is allow the holder to constrain their hold via other scripts, not just via data like pub keys. And that basically works because Nexa has an op exec feature, which basically says, hey, you can, for a limited number of times in order to limit the DOS attackability, you can actually say, hey, execute this little bit of data as if it's code. So the holder can, instead of passing a pub key, it can pass a script that does like a check multi-sig, right? Okay, but that still gets completely isolated out into the holder's arguments, right? So now the covenant just basically says, oh look, the child script template hash matches my known script template. So covenant good, I don't care what the holders, provided as its arguments. That's its problem, right? Okay, and this actually gives you like a whole lot of other interesting features, like not features like optimizations. So notice then if blockchains basically follow the 80-20 rule, or probably more like the 99-1 rule, which is that almost all of the scripts are going to be the same, right? Except for the modifications of the holder, right? So you're either going to have a popular script or you're not, right? So in like pay to script hash, that puts a so, the entropy of the pub key when you hash it creates a script here, which is, like this value hash of script, it's 32 bytes of random data. You can't tell what it is at all, right? But with the script template system, this script template is going to be repeated. The popular ones you're going to see them over and over and over again, right? First thing that we can do is say, hey, in the future, we can just write code that says, for network compression purposes, we can just sort of say, hey, two nodes can agree that certain script templates are, this would normally be a 32 byte number, right? But we can just say, hey, we're just going to, this particular 32 byte number, we're just going to call that number 10, right? We're going to call this one number 11, right? And so instead of passing, these 32 byte chunks, which end up starting to become like a large portion of, the UTXO set, you can even like if you, hard coded them into your code and then into the database, right? You can, reduce the size of the database as well, right? Okay, and in fact, this is what we've also done in terms of consensus. is we've said we're going to reserve some of these IDs to also be part of consensus. So if you just choose script template number 1, what you get is pay to public key template, right? It's a standard script template that we use. And so that is very, it creates a very efficient encoding, right? And then the other advantage to this sort of idea too is not only is it an efficient encoding space-wise, but we could also potentially not even bother to run the the interpreted Nexa virtual machine when we run into script template 1, right? We could actually just hard code an optimized implementation directly in C that runs through, executes that particular script template. Does that make sense? So
Yeah,
now,
of course. It's just like the inception of opcodes. You've got opcodes, which obviously just an optimization of the actual operations the computer has to do into like a single byte.
right.
Yeah, each opcode is just a byte, right? So
Yep.
and then you've just got this, which is an optimization of the virtual machine code, which is compressing a script into a byte,
Yes,
right?
now we can say, we can say script number 1, we're just going to write that in C, right? And it's going to execute insanely fast. Doesn't have to create, virtual machines, launch them, or anything, right? Just boom. So this, well, okay, so, signature validation is always going to be very expensive, right? But, if that is solved, say, with parallel hardware or something, then, this is sort of the next step where we say, well, we don't have to be launching all of these virtual machine environments, even though, don't think of it as running a Linux virtual machine, but it is, you've got to allocate all the space and it's an interpreted language, right? So it's insanely slow compared to just executing some C code, right? So, we can take the most popular scripts, and what's interesting is whether they are hard-coded as numbers or not, we can write optimized versions of them. Because also, as we said, this script template is a constant now, right? It's not a function of, the holder's customizations, right? So if some script template becomes super popular, but we don't feel like it's necessarily fundamental enough to be part of consensus, so we don't assign it like number 2, right? We just leave it as a 32-byte hash. You can still write optimized code that says, oh, if I see a script template of that exact hash, just execute this C++ code, right? Boom. Don't even bother, to actually interpret it. So this can create a lot of speed and efficiency.
Right, I can see this used, like, let's say we've got this constant product market maker like Uniswap on
Right.
Nexa that, let's say there's like millions of transactions happening, but they're all using the exact same script. This is a perfect use case for this because
Yeah.
obviously, it's going to speed things up massively by just having, like you say, like a hyper optimized setup for handling those transactions.
Right. Right. Yep.
Or
And
even
then,
more ideally, maybe have it actually done in the accelerated hardware at some point, if they really are like that, used that much.
yes. So, and I feel like it's like a transition, right? Like, oh, here's an interesting script. Oh, look, it's, a non-trivial percentage of the blockchain and it's a big script. Let's optimize it, right? But we won't, put it in consensus. That we won't assign it like number 2 in consensus, right? We'll just run that script whenever we see this hash, right? Oh, look, for the last year, the use of this script has only grown, right? Okay, let's give it a number now, right? And so now, the blockchain itself, if you choose to use that number to indicate the script template, is now going to be more efficient, right? Space-wise. And then finally, wow, let's create a hardware implementation of this thing, right? Because it's become like endemic, right? And it's not going away. So yeah, I mean, these are the options, and all these things become possible if we can only use, if the script you're running can be identified with a constant, right? And it's not being modified by, hard-coded constants inside the script. So that's why I called it a script template, right? Because templates are like the structure, but then you fill constants in later, right?
Yeah,
Okay.
that makes a lot of sense.
Yeah. So let me quickly look at the notes. Okay. So let me talk about how a script template actually runs, right? So the important thing to say too is, first of all, that the script template, the holder's arguments, and the spender's arguments are all in the transaction that spends them, right?
The inputs.
Yeah, the inputs, and the commitments are in the outputs, right? So really, what you just do is you would check that this script template, the hash of this is actually what was committed to in the output, right? And you check that the hash of the holder's arguments is what was committed to in the output, right? And then you're good to go, right? Okay. So then how you actually execute this is you basically you execute the holders script. And so first step, execute holders script. Okay, and if you do that, you're just going to end up with a stack, right? Because all it's allowed to do is push. And then you execute the spender script.
So just to confirm, because you said you end up with a stack. So does it mean like you can only use the push opcodes with data?
Right. Yeah.
Okay.
Yeah. And the reason why that's the case is because the argument is, hey, all this, like, there's no global variables that will change here, right? So if you need to add two numbers, just do it offline and push the sum, right? So don't have, this virtual machine add, two constants, just do it, right? And everything coming into the script, to the transaction, is constant, because, the UTXOs that suck state in are well-defined, right? So since everything is well-defined, you might as well push the most optimal, your script might as well be the most optimal version it can be, which is just pushing this data, right?
Right.
Okay. And so then the same thing is true with the spender script. But it does not, like in classic Bitcoin, the next script can use the stack of the previous script, right? But this is not the case. Like we don't want the spender to be able to modify the holder's arguments, right? Because then the spender, it would be insecure, right? So the spender executes and cannot see the holder's stack, and it just pushes more data on. It's push only as well. So, for two reasons it can do that. So it creates another stack, and it pushes a bunch of options on more data, right? And then basically, finally, the covenant or template script runs. And in this case, it is given the two stacks. So if you recall, in Bitcoin, there's a main stack and an alt stack, right? And so that's done so that for certain complexity reasons. But boy, it was really convenient that already existed, because basically what I do is load the holder. I got to remember this. Yeah, the holder is pushed to the alt stack, and the spender is pushed to the main stack. And the reason why I did it that way, it didn't really matter which one went where, but because in traditional Bitcoin, the spender goes to the main stack. So I kept it like that. And so then the template script runs, and it uses the alt stack and the main stack, and it can suck, the different pieces of data that it needs off of these two stacks. And then, of course, and remember, the key issue here is that some of the holder scripts, like the holder script here, it could push data that would be something like, it's pushing one big value, which might be something like pub key, and then, check sig, right? right? Or it might push another script that would be like, check data sig, right? So like that. And so basically the template script might say, okay, now execute, this piece of data in the holder script, right? Or now execute this piece of data in the holder script. So the covenant, is like the referee. It gets to decide when other scriptlets run, right? So, but then the holder and the spender can, contribute their own actions by running these sort of subscripts, or sometimes they call them scriptlets. So in this case, for example, the holder is running a check data sig, but it didn't push any data in front of it because it would be relying on some data that the spender pushed, data and signature maybe. And so,
right, and so the template script itself would say, right, first grab this from the main stack, grab this from the alt stack, and like it's kind of like the template script is like the recipe, and the holder script and the spender script is like the ingredients, right?
Yeah, that's a good way of putting it. Yeah, the template script mediates the interaction between these other two scripts, right? And can enforce its own rules.
Mm-hmm.
Yeah. And yeah, so the template script would be like, okay, grab the data and signature from the spender, right? Because this, in this case, say it's a check data sig, so maybe it's like an escrow, right? And it's saying, well, okay, if if someone, if this this trusted third party signed this piece of data saying that this external event occurred, right? Then there's a case where the holder allows that to happen, right? So like, I don't know, like a case where people have considered using this sort of thing is let's say, I mean, it requires some infrastructure, but let's say upon your death, you want to give your coins to your heirs, right? So if someone is out there, like, reliably signing, statements of deaths, right? Then you could, the holder could constrain, its coins against, that piece of data with that, and that sort of third party entity signature, right? And in like classic P2SH, though, that would be impossible because, the covenant script would have had to have anticipated that and be like, oh, well, maybe the holder, right, would want to do that. And I mean, there's no chance that the covenant script is going to anticipate that. But instead, in this case, the covenant script goes, okay, well, I've verified my constraints, which we didn't talk about, but it can just, in a normal way, can have any constraints at once. And now I'm going to say, okay, well, let's just execute the spender's constraints. I'm sorry, the holder's constraints. And that could be anything. That could be multi-sig, that could be check data sig, that could be check sig, right? And so, in theory, I mean, we haven't gone down, these crazy things, but, you might be able to, for example, pack a, another sort of anyone can spend smart contract inside the holder, right? So the holder might be, a constant product market maker, which is inside the holder script of this other, this other smart contract.
Yeah, that's when my brain just reaches its limit on
Right.
like imagining how these things all go together.
Well, no, it's going to be interesting, right? So the question is in like, the Ethereum virtual machine is just a very sort of just like we always program type system, right? And you can have a contract and you can call another contract, right? The question is, in the UTXO model, how do you make contracts call other contracts and things like that, right? And you know, it's going to be interesting and complex to do that because of the UTXO model, which, by the way, has advantages of being massively parallel and all these other things, right? So we're using this for, you know, very efficient, right? So we're using the UTXO model for certain ways. Well, what I just proposed right here is one way that you could have contracts that sort of call each other, right? We're embedding one contract as a scriptlet, a holder scriptlet inside a larger, you know, contract.
Can you explain that like a little more? Like, so I understand what you've explained here with the template script, the spender script, the holder script, and how that's come from the previous transaction kind of going into it by constraining it with the hashes of these bits of information.
Right.
But how would that then allow one transaction or contract, smart contract, to control another one? A separate one.
So it doesn't control it so much as it delegates, right?
Okay.
So you would, so the overarching smart contract in this case says, okay, right? My constraints are satisfied, so I'm going to allow the holder, right, to do a spend, right? But perhaps the holder is not saying, oh, if you just give me your public key, you can spend this, right? Maybe the holder says, well, you can spend this if there are two additional outputs, you know, inside the contract, and the product of those outputs is, you know, greater than this constant K, right? So now our holder is actually a constant product market maker.
I think I understand. It's a tricky one. I feel like I have to sit down and like draw this visually, like how this all gets here, because I understand what you've drawn and explained here. But like how that then works with actual like different entities interacting is kind of just going over my head at the moment.
No, I mean, for sure, like this is like the bleeding edge of exploration here, right?
Yeah.
People aren't like doing this yet, right? So it's going to be like a lot of fun to sort of explore these sort of things. And there are other ways that I don't want to talk about today where you can sort of simulate contracts interacting with other contracts. We can go over those other ways in other, you know, chats, but this is one sort of interesting way.
Yeah, that is very interesting. I'm definitely gonna have to spend more time on it, so I think to understand how like the interactions are different now that there's these three separate entities. Um, I feel like I'm really still struggling with the concept of a holder, though. Um, yeah, I'm not sure why. uh, the holder is the person who actually creates not the transaction, but who puts the constraints on the UTXO. Is that
Yeah,
correct?
yeah, let's think of it this way, all right? Let's think of it like, let's say that we have like some NFTs, okay? And let's just say that like you have this NFT and, you know, it's like, let's just imagine it's some sort of like Pokemon power up like hierarchy, okay? So, you know, you want to have, so the entity who made these NFTs wants to have a clause in there that says, hey, if you get, you know, an NFT of this class and this class, right? And you spend them both at the same time, then you can create an entity of this other class, right? You know, you can power it up and you can level up your NFT, okay? Okay, so you see that is like a referee option, right? That the you know, that the overarching system needs to enforce, right? So that would be in, you know, the covenant, right?
Right, the
Okay,
template
like the
script.
referee doing that. Okay, so now though, there's someone who owns that NFT, and they're saying, you know, well, how do I want to own the NFT? And like, you know, right now, the obvious way is, well, we'll just constrain it by a pub key, right? But maybe these are very valuable NFTs. So, to use the simplest example, maybe that NFT should be constrained via multi-sig because it's actually, you want like a certain security level on that, right? So you don't want anyone who, compromises one wallet to be able to spend that NFT, right? But how could the original sort of referee anticipate that a particular person wanted to hold their NFTs either via pub key or multi-sig, right?
Yes, okay. I get it now.
So
Like
now
it's
the
all
holder
kind of sunk
says,
into place.
right. So the holder now says, oh, I have some, additional constraints on the holding of my NFT, which is it needs to be multi-sig, right? And sure, like we were talking about workarounds, like actually the covenant script could sort of anticipate that and literally make a giant if statement that allows the holder to choose one of, say, 5 canned scripts, right? So people, I'm just saying this to qualify because people will always say, but you could, right? Yeah, you could have it, if and then you allow the holder to choose, right? Or the spender to choose, right? If constrained via pub key, else constrained via 2 or 3 multi-sig, else constrained via 3 or 5 multi-sig, else constrained via 6 or 7 multi-sig. And you could try and anticipate like all of the holders constraints, right? But it's not real like contract interactivity, right? To do it that way, you're just making these guesses, and there's always going to be someone who says, well, that's not the way I wanted to, do
But
my
because
situation.
right, but because it's a hash of the holder's arguments, it gives them full control,
Well,
like
because
over. Yeah, because
those arguments can be a little script, right? And that little
right.
script has to succeed for the full contract to succeed.
Okay, I see. It just adds a huge amount of flexibility. I understand. So the only thing that has to be set up front is the hash, obviously, but because the hash can just be a hash of kind of any data, which ends up actually being
Code
potentially
and data,
full.
right?
What's that?
So in this case, like it's the difference between the data that the holder pushes in like the old style could just be pub key, piece of data, right?
Hmm.
But in script templates, it can be pub key check sig, right? Or it could be pub key check multi-sig. And so then instead of the instead of the the referee, right, the covenant just assuming, saying, okay, grab what the holder pushed and then run check sig, right? It just says, okay, grab what the holder pushed and execute that, right? And so, and it doesn't assume, check sig, check multi-sig, check data sig, right? It allows the holder to, provide a little chunk of code.
Right. Okay, that makes a lot of sense. I think it's really just the term holder that's confused me because I always see the output script as just like a locking script. It
Maybe the
determines
lock.
how it gets locked. Yeah,
Yeah.
it's like a something to do with like locking the person who locks the contract. I don't know what term that would be, but I understand now. I understand how that works. That makes
Right.
sense.
So in your terminology, you have the referee who sets the rules of the game, right? And then you have individual players who lock and unlock, right?
Yes.
And
Yeah.
so in this case, the question is, can the individual players who lock, can they lock via a rule set, right? Like, code, or can they only lock via a pub key, right? Or hard coded data, and the referee has to like anticipate all the ways that the locker would want to lock. The answer with script templates is, the locker can lock with code, right? In whatever way that they choose. Whereas with like pay to script hash and other techniques, the referee has to anticipate all the possible ways that a holder, the lock might happen, right? And you can only provide the specific data, right? Like the settings of the pins on that lock, right? But it
Yeah.
has to be that exact lock,
Right. Yeah, that makes a lot of sense. And forgive me if this is already what you've put on this description, but just come to me that you could then make the lock say, it could be like, I can't work it out the exact contract in my head, but it would be something along the lines of like having a check data sig, check that some specific uh, private key has signed a piece of data, but the piece of data doesn't have to be set up front. So it just could be that they like this pub key can say what pub key can be used. So you could, I'm explaining this in a terrible way, but basically what it means is you could change the pub key that allows it to spend on the fly. The holder can.
Yeah, I see how you're doing that. You could.
Yeah.
Yeah. Yeah.
So
Yeah.
that's pretty
And it
cool.
turns out, yeah, and it turns out that a lot of lockers actually do want to have like a couple of like if then else type clauses, right? To really, if you want to really be robust, rather than hang everything on one pub key, right? You might want to say something like, well, in case I lose my wallet, I have this other, multi-sig, which I've stored in, safe somewhere. So, either let the person unlock it via one pub key or a multi-sig would be a good example, right?
Right.
Yeah, and then
Yeah.
I do like,
Go ahead. Sorry.
yeah, you could even say something like, if the amount is less than a certain amount, then you can unlock via this one pub key, right? So let's say, if what we're playing with just happens to be small amounts so that I can do it with my local wallet, use this pub key. But if actually this contract ended up being large, right, then I want to have to do the multi-sig, right? So there's another situation where you might.
Right, yeah, but like value-based constraints on there.
Yeah, exactly. So that the big spends need to go through, this more effortful, system, whereas the small spends does not, right? Something
Yeah,
like
there's a
that.
lot of really interesting stuff that can be done. Like I always felt that even with script as it was before Nexa, that there was like a ton of unexplored possibilities with it because there was just so few people actually looking at it and working on it. And now with this, like it's unlocked even more. So it's
Right.
very exciting. Yeah, it's very exciting to see like what
So
is going to be possible.
yeah, so I would disagree with that statement. So script will let you do a huge amount of things, but you couldn't do two key things. One is you couldn't access the blockchain itself with like your current transaction in the previous transactions, right? So you had no ability to access data, right? External data. And so it was like, I wrote this article like years back saying, hey, um, Bitcoin is not a Turing machine because it can't actually access its own tape, right? And some people said, well, the tape is the stack, but it's really not in the context of a blockchain, right? So since if you can't access even any data in the blockchain, right, then what's the point of running any code? So, things were very limited. So transaction introspection, has solved that problem.
The
And
transaction,
now,
just a quick one on that. Transaction introspection just works on itself, right? The actual transaction that the introspection is within.
transaction introspection can only look at the current transaction.
Yes. Yeah.
Yeah, so that's not quite true. It can also look at the inputs of the current transaction. So basically, as we were saying in the previous our previous talk, we don't want you to be able to access arbitrary and modify arbitrary data in the blockchain because that becomes a massive scalability and performance issue. But if you can explicitly specify what blockchain data, right, what UTXO state you're going to suck into the current transaction, then you can access that state.
How do you do that right now?
They're just like fundamental opcodes that let you do it.
Oh, already. So you can already point, like you can just point to like a UTXO right now and just get the information about it.
Yeah, you basically say like you say push onto this. There's one opcode that says push onto the stack the output, the previous output of input number one.
Right, but it has to be an input of that transaction though, right?
Right, because so if you want to modify or access state, right, you need to identify that state at the beginning of the transaction, right? And that's like a key optimization so that we know whether that state still exists, right? So yeah, within the so when you're running your script, you cannot dynamically change what blockchain state you want to access, right? But you can pre-specify the state you want to access, not in its data, right? But just by the previous UTXO, right? And then you access it. So see the constraint script though, it says, so the entity who made, like the referee, right, script and the holder script doesn't pick those UTXOs, right? It's the spender that picks those UTXOs. So
Right.
so they say, oh, what state is the spender importing, right? And I'm going to access that state to make decisions.
Okay, that makes sense. And just a quick question, like how much, like where does the information come from in terms of, so the introspection that accesses the inputs, does that get like how much? Like I haven't looked at the opcodes recently for introspection. Like how much information is taken about the inputs or the transactions that create the inputs?
You can access all of the previous output. So,
Right. Right.
yeah, so you don't think of a transaction anymore as like a unit, right? Once it goes into the UTXO set, each output becomes its own ledger entry, right? So you can say, give me, the data from the output that corresponds to input 0, right? Give me the data from basically give me the ledger entry that corresponds with input number 0 or 1 or 2, right?
And if you can you scroll up on the iPad, because obviously I think you put that information there, so it's just useful to see. So that would be the group info, script commitment, the args commitment, and the public args.
Yeah, exactly. Yeah. So
Okay.
in fact, there's kind of like there's a subtlety here, which is kind of how can in terms of covenants, right? So how can a script enforce that it is that like children are itself, right? Because as I was saying, what we do is we compare the hash of the script, right? But you can't hard code the hash of the covenant script in the covenant itself because you don't know the hash of the covenant script, right? At the time when you're writing the script, you only know it when it's done. Does that make sense? It's like self-referential.
Yeah, self-referencing, right.
Yeah. Okay. So the way, so in order for a covenant to enforce that, that the output is the same as itself, what it basically does is it says, okay, give me, my own output, right? Give me the
The output
the
that created me, right.
yeah, the ledger entry that I am running from, right? Oh, and what is that script commitment in that particular output, and make sure that the child that I'm interested in is the same. So that's how you do that. But then if you were, another interesting thing though is you could have a covenant that enforces that other covenants exist on other outputs, right? So we're just talking about that the same, right? But you could say, hey, I want to make sure that that this particular smart contract is running, and its input 1 goes to output 1, But then perhaps this is an interacting smart contract. So also let's make sure that, you know, this other well-known smart contract is running on output number 2, right? In that case, you can just hard code the hash of the, you know, of that, because it's a separate smart contract that's well known.
Right, that makes sense.
Yeah. So there's all that kind of interesting stuff, right? When we start talking about, you know, multiple smart contracts that kind of work together. But all this is, you know, unexplored territory. It's really kind
Right,
of
exactly.
sad. I mean, so the, you know, the state of UTXO scripting was basically drastically, it just came to a screeching halt when, you know, Bitcoin was not willing to make the changes like transaction introspection. Neither was Bitcoin Cash, you know, for a long time, needed to really start investigating these things. So here we are. We should be much further than we are, but you know, with Nexa now we have the ability to start exploring this domain space, really.
Yeah, this is what I've been trying to explain to people in the Next community, and people have been very receptive to it, that just because Bitcoin is very incapable of doing like all of these things does not mean that that reflects on Nexa. It's just that, first of all, there's certain things that are just arbitrarily or yeah, arbitrarily constrained, like the block size, obviously. But then there's just, they just didn't want to add, you know, extra functionality
Right.
on Bitcoin. I mean, there's the, you know, the old story about Vitalik Buterin, where he just wanted to increase the oh, I've forgotten what it was now. Was it just the op oh, I've forgotten what the opcode one. What's the data opcode, or the
Yeah,
opcode
op
that gets
return.
used for data?
Op
Yeah, op
return.
return. He just
Yeah.
wanted to increase op return to like
Yeah.
something still very small.
Yeah.
And instead of increasing it, they decreased it like out of spite,
Right.
and
Because they were
they like
probably
cut
like,
it
oh
in
my
half.
God, someone wants to use this as like
Yeah.
data. So, you know, blockchain. And yeah, so whether the blockchain should carry, you know, arbitrary data or not is an interesting question, right? And, you know, I would say most fundamentally, it should definitely be able to carry the hash of external data, right? And to make an argument that it's going to be more efficient to store that data on the blockchain starts to make no sense at all, given how, like, you know, it's, you know, block synchronization does take time. It's a pain in the butt, right? So how are you going to load that data, right? So you do want to be able to store little bits of data, but certainly Bitcoin people got into, you know, felt very emotional that Bitcoin should be Bitcoin only, right? And like recently, you know, El Salvador has this bond, right? Have you been following the news on that?
Yeah, I mean that's using the federated
Exactly. So
network. Yeah.
yeah, so you stole my punchline, right? It's very telling that actually like the Bitcoin bond, which is a, you know, asset, is not even on the Bitcoin blockchain, right? It's on the Liquid blockchain, you know, which is owned by Blockstream, which controls, you know, Bitcoin, what goes into Bitcoin, right?
Yeah,
So
they hire and pay a lot of the Bitcoin core developers.
yeah, yeah. So that's funny. I guess, you know, assets are really useful, but not for Bitcoin.
Right. Well, we should also explain like what they mean by federated, because federated sounds like a really like good term, like, oh, this is really impressive, but it's basically just a multi-sig wallet of a set of trusted parties.
Yeah,
That's
and
how
so
the coins go transfer between the Bitcoin actual main blockchain and the side chain essentially.
yeah, exactly. Yeah. Yeah,
So
so
yeah, it's just a trusted setup.
right, right. And yeah, we've learned in the past year that untrusted solutions certainly are valuable to have. So, yeah,
Or
that was a
trustless. Yeah.
yeah, I said untrusted, but yeah, trustless is better. Yeah, so that was a real eyebrow raiser. But you know, okay. So anyway, so in Nexa though, we want, you know, the blockchain to be finance blockchain, not just a Nexa blockchain, right? And I feel like that will, dramatically increase the value of Nexa itself, because it's going to be kind of like the first among peers, right? Even though, like, for example, UTXOs carry both, can carry one token, like not just a single unit of a token, but one token type, right? One asset type, and they can carry Nexa, right? But they can't carry, like, one UTXO entry can't carry two different token types. So you see, there's like there's like, again, it's like first among equals. There's like every interaction of that UTXO can, deal with assets and Nexa, but it can't deal with two assets. So you're going to have efficiency, advantages and so forth.
Absolutely, and obviously there's like a ton of advantages in auditability. Like obviously, people may think from this discussion that like using script is really difficult, and to be fair, it is. But it's actually very, very easy to audit what is actually happening in the contract. You just take the transaction, run it through, and what you see is kind of what you get. Like there's no like random things happening, because it's not accessing tons of data from outside of the actual transaction.
Yeah, absolutely. So it becomes a self-contained unit. Exactly.
Mhm. So for financial transactions, that's quite important, obviously, to know
Yeah.
actually what the transaction is going to do.
Yeah. Yeah, good point. Yeah, but we definitely do need to create more higher level languages, which, a BUIP. I think that BUIP passed, right? I voted for it.
Yes.
Yep.
Yeah.
So we got that, and I want to create even more interesting languages. And then I have a little script debugger, which I quickly coded up, which still is just using the base assembly language. But if people need to get on this real quick, they can start using that, and it does support three three entity interactions. You provide the three scripts, and it will execute them.
Yeah, I had to play around with it actually, and now like I was starting to get an understanding of how things work from that, but now after having this conversation, I would say I fully understand.
Right.
So yeah, I think that's going to help me a lot in trying to explain it to other people as well, if we're going to create some like content explaining these things. Because it's like you say, this is a very hard thing to get across to developers how it works, because it's quite new in terms of like the UTXO based blockchains.
Yeah. Yeah. And, it's also new to Ethereum programmers who are used to just, hard coded contracts, and they just, cast a, I mean, they're not really hard coded, but once they're in the, you create a contract, it deploys to Ethereum, you get a big number, right? You cast that number to, the contract, and you call an API on it, right? So that's very much like JavaScript programming, right? Whereas this is going to be a little bit more interesting.
Yeah, I'm definitely interested to see how the kind of interface with this can be kind of abstracted to a point where it's very obvious how everything kind of interacts with each other.
Yeah. Yeah. One thing that I'm interested in, which I don't see Ethereum doing, but you already see that in sort of my website and so forth, is partial transactions, right? So this lets you do is stuff like, hey, you partially create a transaction, and it's maybe fully signed, but it doesn't balance, right? Or maybe it's not fully signed, and you ask for someone to complete it and then pass it back, and then you sign it, right? So you can kind of throw these things out, and you almost have like interactive transaction completion protocols, which then implement stuff like more complex operations, atomically.
Right, absolutely. I mean, the only kind of type of transaction I know that's used like that is the crowdfunding type transactions, where you set the outputs, you kind of lock the outputs, and then everyone has to add inputs until it reaches a certain amount.
Right. So
That's a fairly simple one, obviously.
right. So in my NFT site, I'm using this create like a committed bid offer, right? So you basically input the NFT into the partial transaction, right? And you output some NEX, and you sign that, right? And you chuck it out there. Now, if anyone else wants to input the proper amount of NEX, into the same transaction, and then output that NFT to wherever they want it to go, they can complete the transaction and sign it, right?
Yeah, that what you just explained, because I've been thinking a hell of a lot about how we can actually build it, like an automated market maker or a prediction market or a DAO with voting and like all of these things. That interaction seems to be like the standard interaction that will be at the core of all of these things, where you have at least two like transaction or inputs coming in with different assets, and then at least two coming out the other side as well. And you
Right.
have it done in a way that, yeah, like you say, that kind of once everything aligns, then it's possible to happen.
Yeah, and this kind of goes full circle to, how you were saying that Bitcoin script is so powerful, right? But the other thing that it's missing is like nouns, so nouns as in assets, right? With Bitcoin script, you have one asset, Bitcoin, right? So, think about actually trying to like go about your daily life, but the only thing that you can talk about is like the only noun you're able to use is the word I, maybe, right? You can't say, I would like some food, because food is a noun, right? You can just say like I food, right? I mean, it's not a language, I mean, you could just say I want. You can't even say that you're hungry, right? So
Right, the
without,
interaction is always sending something somewhere, but it's not
yes,
a trade or an exchange of any
it's not
kind.
an exchange, right? And it's also just it's an incomplete language without nouns, basically. The two things cannot interact. So yeah, like without that, there's no value to smart contracts. So this is why group tokenization was so important.
But it's
Okay.
pretty exciting now that we actually get to see all this stuff come together.
Mm-hmm.
So, is there anything else that you want to discuss more about script templates? I think that was a very good kind of
Okay,
summary of
good.
how it works,
Yeah,
or
no, that's
at least now I understand it. So,
right. Right.
okay, so that's like a good point to wrap it up. I think that was like a deep dive into script templates and smart contracting on Nexa. Obviously, this is very low level stuff, and like you say, there's a new smart contract language that is going to make things a lot easier, although it won't be fully complete. It won't allow you to do everything, and then over time, the plan is to build up to something that really allows developers to kind of do anything that's possible on Nexa.
Yep. Yep.
So thanks, Andrew, again for the chat. Really appreciate you taking the time again.
Okay, great. Thank you for being the other side of these.
Yeah, and thanks for listening, everyone. If you have any questions about any of this stuff, of course, just chuck it in Discord or Telegram, and we'll try and answer there. If not, we may ask them questions in future discussions like this. So yeah, thanks everyone, and we'll chat to you again in the future. Bye.
All right, bye. Great.